Image edge detection. How does it work? There are various mathematical methods for identifying points in an image where the image brightness changes sharply, or more specifically experiences discontinuities. The method discussed today is the Canny Edge Detector. So this is a multi-stage algorithm for grayscale images. There are 5 steps associated with the Canny Edge Detector. The first one is going to be noise reduction. The second one is gradient calculation. The third one is non-maximum suppression. The fourth one is double thresholding. And the fifth one is hysteresis. After that, we're done and we have all our edges from our image. So let's go through each one right now. Step number 1 is noise reduction. Here, we see that edge detection results are easily affected by noise in the image. Hence, blurring the image would be effective to reduce noise. Recall the Gaussian blur from the previous image blur video. We can apply the Gaussian filter kernel and convolve it with the image. Typically 5x5 kernel sizes are used for the Canny Edge Detector. If you haven't watched my previous video, or still not sure about how Gaussian filters work, feel free to pause this video and look at this slide where I teach you a little bit briefly how to perform kernel filters. Step number 2 is gradient calculation. An edge in the image typically points in a particular direction, and the use of an edge detection operator can be applied to find such direction. There are numerous operators including Roberts, Pruitt, and Sobel. We will focus on the Sobel operator for now. The Sobel operator can be used in image processing to create an image emphasizing edges. The algorithm uses two 3x3 kernels for the vertical and horizontal directions, and later uses A10 to determine the gradient's direction. So here we have two different kernels, as we can see here, the vertical and the horizontal. We can tell clearly that if we convolve this with an image, then if there's a particular border on one side, we'll get a large magnitude, because the value is gets outweighed by one side versus the other. So in order to compute the magnitude, we use this formula over here, which is the distance formula. In order to get the direction, we use the trigonometric A10 operator, which is inverse tan of gy over gx. Here's an example of the Sobel operator in action. We have this image and here we get these nice contours, and we actually already have edges. But if you look more closely, some of them are thick, and maybe we'd want to get more precisely what the edges are. Now how do we do this? This will be the next steps. So non-maximum suppression, step number 3. So we want to have thin edges, and we want to eliminate fades on either side of the edge. The idea is simple. Take the direction of the edge, which we got based on the gradient determined by the Sobel operator, and verify both ends of the vector extending outwards from the gradient. If either end of the vector is greater in intensity than the current matrix index, you discard the value entirely and set it to 0. So what does this actually look like? So, we have this matrix 3x3, and we're going to consider the middle element inside this matrix. So we do this process for all the different pixels. We look at the gradient and we get the angle. So for this pixel, we see that we get a vector that looks something like this. This is the direction of my edge. I'm going to be looking at the pixels that are on either end of this vector. So this would be the gray and then the white. We have these 3 pixel values, and let's sort them by intensity. We see that one of them is actually more intense than my gray value, right? So since the white value is more intense, I set this to 0. And now we effectively make our edges thinner. So this is non-maximum suppression. Step number 4 is double thresholding. We now further classify all pixels into 3 categories. A strong pixel is a pixel that we can confidently include in the final result. A weak pixel is a pixel that has an intensity value that may be enough to be considered strong, but not always. And the irrelevant pixels we should immediately discard and set the value to 0. So how and why do we do this? So how do we select these arbitrary thresholds of what makes a pixel strong and weak? Typically, it's empirically determined and depends on the content of the image, so there is no fixed answer. So why do we do this classification? It's used as a pre-processing step for the hysteresis edge tracking algorithm, which is the next and final step. So for this step, we're going to recall the classification of pixels we developed in the previous step. We keep all the strong pixels the way it is and discard the irrelevant pixels just as before. But for weak pixels, we consider the pixel neighbors around the pixel. If one of the pixels is considered strong, then we keep the pixel, otherwise we discard it. So, how does this actually look like? We have this image, and then let's say we're considering the gray. Gray means it's a weak pixel, white means it's a strong pixel, and black pixels we already discard. So we're going to be focusing on the middle pixel, the gray pixel. We take its neighbors, which are now in pink, and we notice that one of them is a strong pixel, so we're going to keep it. Now, if we look over here, we look around all its neighbors, and all of them are weak pixels. So then we're going to discard this one, and this one will be black. Thank you all for watching.